I guess today and tomorrow I'll talk about stuff that I've been doing for the last like 3 years, I guess, um, with Mykola Dedushenko, Ron Jacobi, and Yael Fan. And tomorrow I'll also talk about some other paper. So the motivation or introduction is the following. Quantum field theories have some fundamental observables, which are local operators, can be inserted at any point x. And we can compute their correlation function. So O1 of x1 through On of xn. This is great, but in more than 2 dimensions, there are almost no interacting QFTs for which these correlation functions are known exactly. So because of that, it would be interesting to figure out what are the cases where they are known exactly. Okay. So what are the exceptions? As far as I know, all of them involve supersymmetry in 4 dimensions. There's some protected operators in n equal 4 super Yang-Mills theory. Protected means that there are some correlation functions of these operators don't depend on the gauge coupling, so we can compute it at weak coupling using weak contractions, and then that's the result of strong coupling as well.
You think of 3-point functions?
For instance, 3-point functions, yes. And there are also generalizations for n equal 2 superconformal field theories. This is the chiral algebra story developed by Leonardo Rastelli and collaborators. Then, in all various numbers of dimensions, one can compute 2-point functions of operators related to conserved currents or the stress tensor, related by supersymmetry to these things. So this is in various numbers of dimensions. And then there's another example, which is Coulomb branch operators in 4D n equal 2 theories that I wrote a paper on with Zohar, Komargatsky, and Jaume Gomes, but I won't talk about that. So what will I talk about? Well,
that was like in the NF equals 4 SC2 theory. That kind of thing.
For example, yes. Or NF equals 2NC. So in this talk, we'll do 3D, since most of those things are in 4D. 4D, n equal 4 superconformal field theories. And I'll talk about correlation functions of half BPS operators. There are some non-conformal generalizations, and I might mention some non-conformal generalizations at the end. Yes, that's right. Right. Well, I can mention the relation to that work.
Just to get an idea, notation.
Yes.
N equals 4 means how many supercharges in 3D when you use the notation?
Good. So the maximal is n equal 8. So this is half maximal. So the superalgebra is OSP 4/4 that has 16 supercharges. Half of them are Poincare supercharges, half of them are superconformal charges. Okay. So, well, you could ask why study this example. Well, like, why study any example, computer correlation functions? This, in supersymmetric theories, these things could be toy models for more realistic examples. They could be relevant for AD-SCFT, and I'll mention some of that tomorrow. If we can compute some of these correlation functions or OB coefficients analytically, this could be an input for more complicated calculations, such as conformal bootstrap. We can use these things to find new dualities, and we did in this case, using the formulas that I'll show you later. So anyway, that's the motivation.
The simplest examples of these theories are like bifundamental kind of theories?
No, I'll tell you. Yeah. The simplest example is a free hypermultiplet. Interacting example is like a gauge theory.
Gauge theory with what?
With a hypermultiplet matter, any gauge group.
Probably or before baby jam or something. Reduce the.
Right, you could also do that, but that's a complicated example. There's
That's what I was
much simpler.
All right, good.
Just gauge theory, n equal 4 gauge theory with some hypermultiplet matter. Any gauge group, any matter representation. The matter representation must be big enough for the theory to flow to a superconformal field theory.
So you just start in the ultraviolet with the what I would have called 4 supercharges.
Yes.
And then you flow.
Oh,
You read a superconformal.
8 supercharges. It's 16 total, 8 Poincare, 8 superconformal.
Eight,
Yeah.
eight, and then
Yeah.
flow.
Yes,
Are
that's
you,
right.
Are you generically going to look at theories? Sorry, you tell us, but the theories that violate parity, will they have Chern-Simons terms in the
The
IR?
theories that I'll look at won't have Chern-Simons terms.
That's why this one. Okay. That's fine.
It's actually very interesting how to generalize this for theories with Chern-Simons terms.
Yes.
I can tell you what one obstruction is.
So it's the
but
analog of like the D2 brane theory. I mean, the IR of the D2 brane.
that's right. Yeah, maybe with some extra higher dimensional brains so that we can have like flavors. Okay. So 3D n equal 4 superconformal field theories. Contain miraculously 2 1D topological sectors. What that means is that there are some operators in these theories that we can construct, and I'll explain the construction, where if we put the operators on a line, we can put them anywhere on this line. The correlation functions only depend on the ordering of the operators on the line. They don't depend on the relative separations of where we put the operators. This can be understood abstractly, and I'll also give examples. So first, I'm going to explain abstractly how this works. Okay, so all you need to know is that the superconformal algebra, which is OSP 4/4, that's not that important. What's important is that it has as a subalgebra the conformal algebra, which is SO3, 2 in 3 dimensions, and some R-symmetry algebra, which is SO4, and I'll write it as SU2H times SU2C. H is for Higgs, C is for Coulomb. If we have operators, the operators are labeled by their quantum numbers. For the conformal group, we have the scaling dimension and the spin. For SU2H, we have the SU2H spin, which I'll call JH. And for SU2C, we'll have the SU2C spin, which we'll call JC. just as a matter of notation, when I'm going to be using SU2H spinor indices, and those I'll denote by A, B, C, and so on. So they take values 1 and 2. And for the SU2C ones, I'm going to use A dot, B dot, C dot, and so on. These also take values 1 and 2. OK, these theories contain generically 2 types of half BPS operators. Oh, I don't want to erase my vertical line. So the half BPS operators are of 2 types. One type is what I'll call Higgs branch operators. Abstractly, there are scalars. They have the scaling dimension equal to the SU2H spin. So delta is equal to JH. And JC equals 0. They're invariant under SU2C.
So JH normalized like half, 1, 3 halves?
Correct, yes. Simplest one is half. So this operator in general will look like, it will have, I can think of it as a symmetric tensor of rank 2JH. So it could have indices A1 through A2JH, and it's symmetric, and I can put it at any position X.
Maybe the mic.
Yeah. Either ICTS or HRI may have their mic on, so we'll request you to put it off until you have questions.
The all mic is off.
Okay. ICTS, could you check if your mic is off, please?
They didn't even hear us.
Yeah. Okay, let's go.
OK.
Thank you.
And the other type is Coulomb branch operators, which are scalars. They have the dimension equal to the SU2C spin, and they're invariant under SU2H. Everything in these theories is symmetric with respect to, so if something happens for SU2H, there's a mirror dual that happens for SU2C. So these operators would be A1 dot through A2JC dot, and we can put them anywhere at any position.
So free scalar that transforms in the doublet of J is a candidate supersymmetric operator.
Correct. That will be my first example.
So you have free scalar, so which delta equals J
Oh, half.
equals
Yeah,
half
yeah.
is
And it's
It
a,
transforms in the doublet.
it's a doublet of SU2H.
Yeah.
OK, maybe I can erase this. So, OK, so these are 3-dimensional operators. I promised that there would be operators that we can put in 1 dimension, such that the correlation functions are topological. So I'll construct them from these ones. So there's 2 topological sectors, one constructed from these operators and one constructed from those operators. So let's just do the first one first. The Higgs branch 1D
Sorry, if you don't.
operators, yes.
In the D2 brain theory, or the M2 brain theory, if you use a convention in which the supersymmetry transforms like the vector of SO8, then the scalars transform like a spinor of SO8?
Yes.
Okay, so this is the analog of that.
OK. 1D operators. So let's just say that we put them on a line, and the line is in the parameterized, so the line is parameterized by a coordinate x, and it's 0, 0, x. So it's in the x3 direction. So then O of x is given by this expression, u a1 of x through u a2j of x, 2jh, I guess, if it's Higgs, times this operator O, a1, a2jh, inserted at 0, 0, x. Where I didn't say what u is. A, so A is 1 and 2. So if A is 1, then this is 1. And if A is 2, this is x over 2r. So we're contracting the SU2H indices with position-dependent functions. So what are we actually doing? Well, we take this when all the indices are 1. We don't multiply it by anything. And then we take this when some of the indices are 1 and some of the indices are 2. And then we multiply it by x over 2r to the power the number of indices equal to 2. And then we add them all together.
What is R?
R is a parameter that I have to introduce such that dimensional analysis holds. So x has dimensions of length. R will also have dimensions of length. Okay? So R is just a parameter for now. I mean, it will always be just a parameter.
And 1 and 2 have particular angular momenta under rotations. Is that the z-axis?
This is the z-axis, yes, correct.
So 1 and 2 have angular momentum plus half and minus half under rotations around the z-axis.
No. 1 and 2 are just the, these are the SU2H indices.
Sorry.
Yes.
So you've just chosen the axes in space at random.
Yes, the axis in space is chosen at random. I could have chosen it to be anything else.
Yes, sir.
The whole point is that when I choose my axis, I just have to multiply these, contract these indices with these polarizations that are defined like this. This isn't the only choice. I can make SU2H rotations on this, and I will still get a topological operator, but this is a choice that works.
I'm sorry, I'm still missing something.
Yes.
So we have a scalar. You're doing the example with, say, a scalar, or is it?
Yeah,
at the back of our minds, at least?
yes. Do you want me to do it now? I can do it now. I was going to do it in a bit.
What are these operators O of x? I haven't quite understood. So if you
Which one? These ones?
scalar case, right? Okay, theta. So they have these indices which go from A1 to A2H or A. What is it?
Yes, 2JH,
It's a product of two J8 symmetric scalars.
for example.
That's what it is.
Yes.
But they are inserted at separate points, right?
No, they're inserted at the same point. This is the composite
Composite
operator. Yes.
Okay, now I'm with you. All right, thank you.
Okay.
Got it. Okay.
Okay. And there's the Coulomb branch 1D operators O of x, which are constructed in the exact same way. VA1 of x, VA2JC dot of x, multiplied by the operator OA1 through A2JC, that's 0x, where we can take this V to be the same thing, or we can take it to be something else that's related to it by SU2C rotations.
R has to be the same.
R is a parameter, R is arbitrary, you can just
No,
take
in these two cases.
a.
You want these sectors to exist together, right? As topological sectors.
They exist I'm not going to be studying them together. I'm going to be studying them separately. I can choose some R for this one. I can choose some R for this other one. It's not going to matter. Yeah, an example would be illuminating.
No, sorry, Sunil.
Yes.
Yeah, so if you had, you don't want to insert Coulomb and Higgs together on a line.
No. I'm just either going to do the top one or the bottom one, not together. Together, they're not going to be topological. So the claim is that only if I take as many operators of this type that I want, I can insert them on a line. The correlation functions are going to be topological. Same from here. If I mix them up, the correlation functions are no longer topological.
Right, and you keep saying you can do SU2 rotations on these.
Yeah.
You can also do SO3 spatial rotations on these.
I can also do SO3 spatial rotation. So I can put, yeah, that's right. That's right.
But if you,
Sorry. But all the operators will literally have to be on a line, right? If I understand.
Yes.
You can also
Or
I mean,
because it's a
some can't be along the x and others along the y.
No. They have to be on a line. But because it's a conformal field theory, I can take the line and I can conformally map it to some other shape, like a circle, and I can also put them on a circle, and it will also work.
Okay. I see. Yeah.
but if these groups, let's say I put them together in groups and take the groups very far away,
Yeah.
then would they be separate topologically in that group and topologically in that group?
You mean I take a bunch of operators from here, I put them somewhere here, and I take some other bunch?
Coulomb branch there.
Oh, Coulomb
X
branch far
here
away.
and the Coulomb branch operators here, very far away from each other.
Oh, geez, okay. I'm not 100% sure. I guess so, because correlation functions will decay.
Sorry,
But anyway, I'm not going to do that. Yeah.
One more
Yes.
stupid question.
Sure.
This is about the origin. The origin here seems to play a distinguished role in your use
Yeah.
case.
Yeah.
But there should be translational invariance
Um,
because you can choose your origin wherever you want.
that's right.
So that seems to say that if I shift x by a,
Yeah.
nothing matters, nothing changes. I can't immediately see that.
That is true. That's what's going to happen. Yes.
Okay.
Well, first of all, let me tell you the reason why the correlation functions are topological. It's going to be brief, and then I'll give an example, and that's going to be perhaps better. Okay. So yeah. So the claim is that O1 of x1, On of xn depends only on the ordering of xi, and of course on the what operators these are if they're different. The reason, conceptual reason, is that these operators O of x are invariant under some supercharge that I'll denote by Q. This supercharge is schematically of the form Q plus 1 over R times S, where Q is a particular Poincare supercharge and S is a particular superconformal charge. And furthermore, so there's Q invariant, Q squared is 0, so they're in the cohomology of this supercharge. And there's an important property, which is that translations in X, which I'll call P hat, these are the usual translations. So translations in X, in little x for little o, it's not just, that doesn't just mean that I'm translating this operator. I also have to change the polarizations. Therefore, the translation in X is the regular translation in the third direction plus an R symmetry rotation. As I'm translating, I'm changing the 1 indices into 2 indices. So this is Q exact. So this is Q of something. Then abstract argument. So this O of x.
Translation in each individual x?
This is the translation operator.
For all of them together?
No, because
Individually?
well, it's going to work individually just because they're all Q invariant.
I see.
So okay, so this is O of 0 e to the minus I p hat x.
Q square or whatever will act on each operator, right?
Right. So you translate any one of the operators and the correlator will not change.
Will not change. Yeah, that's right. So this is the abstract argument that shows that it's topological.
Q exact.
The-
Q.
yeah, it's important that the other guys are.
Around and it's
That's right. It's important that the other guys are Q close because otherwise this wouldn't work. Okay, and now so this is the argument.
Why P hat was Q exact? Can you see it from this construction?
Oh no, I mean this is just a property of the supercharge that I'm choosing. So I would have to tell you precisely what the supercharge is. I'd have to define my conventions for the superconformal algebra very carefully to show you that you can find such a construction.
So this is, so once I am given the algebra, I can construct one particular Q exact operator.
Sorry, say that again?
You have the algebra.
Yes.
You construct a particular Q exact operator, which is P hat.
Correct. Yeah. So I find the claim is that in this superconformal algebra with P4/4, I can find a supercharge that looks like this, such that Q squared is 0, and such that this P hat is Q of something.
Yes, this is some particular operator which is Q exact. Now, the second claim is that this operator translates X.
Correct.
This depends on the
No, translation operator always, well, P is a translation operator that translates X.
But translates in this twisted way, right?
Translates in that twisted way, yes, correct.
Because of the.
Because of our symmetry. So if you calculate this quantity over here, what you'll find is well, if you calculate this quantity and use the fact that O of 0 is O with all indices equal to 1 at 0. So if you put this in and you compute this quantity, you'll find exactly the expression that I wrote down.
In your P hat, the R part, the R2 one, the
Yeah.
the asymmetric rotation. Why isn't that multiplied by 1 over small r?
1 over R.
Oh, I'm sorry. Yes, dimensional analysis. Thank you.
I'm sorry, I'm going to ask you Neil's question again. Again, anal, but let me ask.
Yeah, good.
Okay. Changing the x here changes this u operator.
Yes.
By changing the second component a little bit.
Yeah.
Now, I'm not saying that that is the same as an R symmetry rotation. That's what you seem to be saying there, right? That you're translating and you're R symmetry rotating.
Yes.
So the translation does the translation. The R symmetry rotation should account for the change in u.
Yeah.
Why isn't the change in u changing the 1, for instance, if x was finite?
Okay.
That's what you asked, right?
Yeah, I have basically in some sense that's the same question.
Yeah, same question.
So we need to compute the exponential of this generator.
Yeah, sure it's a complicated calculation, but I was just wondering if intuitively you could see it. I mean, roughly.
The polarization vector is getting rotated, right?
It's getting rotated, changing x is getting rotated, is a rotation. I can't see
Yeah,
that.
because maybe the norm is changing also,
Huh.
but that's also rotation.
It's also a rotation, but what about the analog of the changing of the norm? I mean,
That you
what
that
is
you can.
special about the second component? It's true, it's changing direction.
Yeah.
But it's also changing both components. Do you have to renormalize something?
No, you don't have to renormalize. The claim is that if you do this exercise, that's what you find.
Okay, fine.
You'll see it better as a rotation when we talk about the sector defined on a circle as opposed to on a line.
I'll tell you again what I'm finding unintuitive.
Yes.
The top component and the bottom component of the spin are basically symmetrical. And you're saying the rotation is changing only the bottom component, not touching the top component. I can't see how that can happen.
Oh, sorry. This generator here is R21,
R21, thank you.
which is a matrix that has only one element equal to 1. Maybe this one. Let's see.
Okay, that makes a lot of sense.
Okay. So we just have to take powers of this matrix.
It's like a sigma plus or sigma
That's right.
minus.
That's
Now I
right. That's right. Okay, good. So, okay, example, free hypermultiplet.
R can be taken to a smaller and with something more familiar.
When you take a little r to infinity, yeah, all the correlation, well, the limit is a little subtle. So after you do this twist, if you take r to infinity, then yeah, all the correlation functions will go to 0 because all the correlation functions, you see, r takes care of the dimension. So if I start with some operators in 3D of certain dimensions, the correlation function is going to decay like 1 over the distance to some power. If I do this construction that I just erased and make the topological operators, that correlation function of topological operator is going to go like 1 over r to the same power.
Okay.
So r just keeps track of the dimension of the operators from which the 1D operators came from.
Can I also think that if R goes to infinity, then the operator will be space, it will be independent of x.
Yes.
And then it will be pointing only in the plus direction, and then you have a selection rule.
That's correct. Yeah.
Just to be totally sure, so the statement that this p hat operator translates in x is specific to this class of operators.
Yes. Okay. Free hyper. So this has 4 real scalars. I can make them.
Sorry, I'm sorry to interrupt you. But is it clear from your argument that you cannot translate through another operator? I suppose it's clear.
Yes, there could be contact terms. So free hyper has 4 scalars. I can make them, I can write them as 2 complex scalars, q sub a, where a goes from 1 to 2. And I also have their conjugates. Actually, the conjugates are going to be, so qa conjugate is going to be q tilde upper a, where I raise and lower indices with the epsilon symbol, because this is SU2. So then the 2-point function, if I write it as qa of x, so it's qa of x1, q tilde b at x2. This is given by minus epsilon ab divided by 4 pi x1 minus x2, where in this convention epsilon 2,1 is 1, epsilon 1,2 is minus 1.
That's simply the statement that it's dimension half.
This is simply a statement of dimension half, and that this is an SU2 index, because this is the SU2 invariant tensor, an SU2 invariant tensor. So the reason why this is an example of the construction before is that both qa and q tilde a have dimension equal to jh equals to 1/2, and jc is 0. So they are the type of 3D operators that I can use in order to make these twisted operators, which I will write as q of x. So this is going to be q1 at 0, 0, x plus x over 2r q2 at 0, 0, x, and q tilde of x, that's going to be q1 tilde at 0, 0, x plus x over 2r q2 tilde at 0, 0, x. Okay? And then you can compute, okay, very explicit 2-point function, very explicit definition. You can try to use the definition and the 2-point function to compute the 2-point function of capital Q and capital Q tilde. Q of x1, capital Q tilde of x2. If you just plug these formulas in, what you're going to find happens is that this is going to be minus x1 minus x2 divided by 8 pi r, absolute value of x1 minus x2. So in the denominator, because of this, we have absolute value of x1 minus x2. And in the numerator, because of these x's over here, and the epsilon symbol over here, they arrange such that in the numerator, there's x1 minus x2. So this is a minus sine of x1 minus x2 divided by 8 pi r. Topological correlation function is like magic. So all other operators in the 1D Higgs branch sector of this theory are simply just products, q to the n, q tilde to the m. Their correlation functions are topological because we can just compute them using Wick contractions. We can compute them using Wick contractions either with this propagator before we twist, or simply with just this propagator that's simpler.
So the jump in this 2-point function as x1 crosses x2 can be understood.
The jump is related to the, well, to the normalization of this operator, I guess. I don't have any other interpretation for it.
So these contact terms you were talking about?
Yes.
And could you say that there's one identity that fails when two operators come out of each other? Let's get
The Q exactness, sorry, the fact that they're invariant under translations only works if the operators don't pass to each other.
Right. And could you see the violation when one comes on top? You know, like the contact term in a word identity.
I assume maybe that should be possible. I haven't done it. I haven't thought about it like that. Yeah. Okay, good. So, in more general theories, (3D) theories, and here I'll just explain the class of theories that I'm going to be discussing, which are gauge theories. Yeah.
Slightly tangential question.
Yeah.
So if he has this is the x direction that you're singled out.
Yeah.
Now if
Or
I take the
Z
y
direction.
direction, supposed to be,
Yeah.
is the SL2R that acts on these two dimensions, or rather SL2C,
Mhm.
is it preserved with the twisted p hat, let's say, as being part of the algebra?
Sorry, what?
Uh,
Yeah. So you want to take something on the x direction, something on the y direction?
If I don't do all that.
Yes.
This kind of thing.
Yeah.
Then there is an SL2C, the conform group that would act on
Okay.
a
Yes.
on a
Yes.
space,
Yes. Yes.
on a particular slice.
Yes. You're asking that's preserved by the supercharge?
Yeah, a twisted version of it, let's say, is it preserved?
Twisted version of it, whether it's preserved, I don't think so. I don't see any reason why it would be. Yeah. You're asking if there's like a 2D theory?
Yeah, some version. I mean, whether this structure, if I take the operator, put it slightly away in the transverse direction.
Yeah.
You know, usually things depend on cross ratio, right?
Yeah.
So should I still have that? Do I still have the fact that things do depend? The 4-point functions will depend on cross ratio such that when they are aligning, they become independent or something like this. So in other words, they depend
Yeah,
on
my-
the cross ratio through a combination of variables.
All I know is that when they're not aligned to be on a line, then the correlation function is very complicated because the correlation function in the conformal field theory you just multiplied by these powers of x. And when it's on, only when it's on a line, the simplification happens.
And also, these operators are not position independent.
Yeah, so that's why
Yeah.
I wanted to use this p hat generator as a part of the SL2C.
Okay, so the most general class of theories that I'm going to be discussing are gauge theories with gauge group G and a hypermultiplet in representation R of G. That means that Q transforms in R and Q tilde transforms in the conjugate of R because Q tilde is the conjugate of Q.
Group is simple.
Any gauge group.
Any group, so it could include by.
Any gauge group you want, any representation you want doesn't have to be reducible.
No, I was just coming back to the comment you made to Shiraz that it won't apply to Chern-Simons theories, and I'm wondering, so far it's all been symmetry, so at some point you put in more, is it?
Yeah, this is the point where I'm saying that there's no Chern-Simons interactions because a theory with a Chern-Simons interaction cannot be written like this, unless it has some sort of dual description.
Can be written with the gauge group, can have hypers.
Yeah, but that you have to have, you see, there's vector multiplets and twisted vector multiplets, and hypermultiplets and twisted hypermultiplets, where you just exchange the roles of SU2H with SU2C. I think you might need both in order to construct a theory with Chern-Simons interactions. I can say it another way. Yeah, let me say it another way, because maybe that would be good. The vector multiplet in an n equal 4 theory has a gauge field and also has some scalars.
Yes.
One scalar is phi a dot b dot. It's in the 3 of SU2C. And the other scalar is dAb, which is in the 3 of SU2H. Okay? This is usually, if we write a Yang-Mills term, this would be an auxiliary scalar. And fermions. A Chern-Simons interaction involves a dA but also some interaction for the scalars. So this is going to be a dimension 1 scalar, and this is going to be a dimension 2 scalar. To make the action conformal, we have to take a product of a dimension 1 scalar and a dimension 2 scalar. But the problem is that they have different indices, and we can't contract them. So we cannot write down the Chern-Simons term.
Which preserves your symmetries, is it? Or
That's right. So we would need a different kind, for instance, we'd need a different kind of vector multiplet for which this phi has A, B indices and the D has A dot, B dot. And then we can take a vector multiplet of this kind and a vector multiplet of the other kind and multiply the phi of this vector multiplet with the D of the other vector multiplet. And then we can have a Chern-Simons term.
But does it necessarily mean higher supersymmetry? No.
No, you can have n equal 4 theories with Chern-Simons interaction.
Symmetry-based argument will still go through, right? I didn't quite get what was the obstruction again.
Yeah, the symmetry-based argument will go through. That the topological construction is still going to be true. But from this point on, I'm not going to be discussing theories with Chern-Simons terms because I won't only want to discuss theories of this type.
Yeah, but the topological sector does exist.
The topological sector does exist, and it would be extremely interesting to figure out how to do what I'm going to describe that we do for the theories of this type, to do it for theories with Chern-Simons terms.
that's exactly what I was conceptually seems.
Yeah. Okay, good. So the action, for these theories, the action is just kinetic terms plus kinetic term for the hypermultiplet, and also Yang-Mills term. And it's supersymmetric completion. Okay? And I'm going to assume that in the infrared there's a superconformal field theory that intuitively can be thought of as just the G-Yang-Mills goes to infinity limit of, obtained in the G-Yang-Mills goes to infinity limit of this action, because G-Yang-Mills is dimensionful.
And
in
I'll
this
ask
case.
a remedial question here. Is it clear that that's what the IR behavior of these theories should be? Is there some law about this, or is
Yeah, you can prove it when the dimension of the representation is big. So, for instance, when we have lots of matter fields of some type, we can do a 1/NF expansion. We can show that,
Yeah.
and presumably that's going to hold down to some value of NF.
So, sorry, what was the question again? The law is that you flow over a fixed line. And how
To,
well do you know
that's right. Yes, but it's true. It could be that for small values of NF, then this doesn't happen.
in which case it could become a gapped theory?
Or there could be some spontaneous symmetry breaking or something. Yep. Okay, good. So in this class of theories, the Higgs branch 1D operators.
I'm sorry, is this law specific to N equals 4 theories?
No, it applies to even non-supersymmetric theories.
So the 1/NF expansion.
Yeah. Okay, so the 1D operators in this case are gauge invariant products of Q and Q tilde, the Q and Q tilde that I defined before, that are constructed from the Q and Q tilde of the hypermultiplet. But now when we can't take any products because they have to be gauge invariant. And these are all the 1D operators in this theory. And for the Coulomb branch 1D operators, these are, so if you recall here, I wrote down what the fields of the vector multiplet are. There's a gauge field. There's this phi A dot B dot. There's DAB and fermions. And I did say that phi A dot B dot has dimension 1, flows to dimension 1 operator.
I'm sorry, and when you say big enough representation, you mean enough flavors of a particular type?
Not necessarily of a particular type. I think it should work in general, but yeah, the calculations that I know in the 1/NF expansion are for a flavor of a particular type. Okay, so I said that this has dimension 1, and it's also in the triplet of SU2C because it has 2 indices. So it has JC equal 1. So from it, we can construct a 1D operator, which is phi of x, which is V A dot of x, V B dot of x, phi A dot B dot. So that's one of the operators in the 1D sector. And the other operators are monopole operators So we can construct the topological operator. B would be the monopole charge. And this would be VA1 of x, VA2JC of x, the monopole operator A2JC of 0, 0x. Monopole operators are complicated objects in these theories. They transform, so they have some scaling dimension. They have BPS ones. There exist have BPS monopole operators. They have scaling dimension equal to JC, such that we can construct these twisted operators from them. But the scaling dimension, or J sub C, they depend on both the monopole charge and the matter content of the theory.
This is because there are zero modes.
That's right. So let me not discuss monopole operators yet. I think maybe we'll leave that for tomorrow. So first, today, maybe I should tell you the Higgs branch story. Okay? So question, is there a Lagrangian or an action or a partition function for the 1D sectors of these theories? You know, there's a Lagrangian for the full theory. Is there a Lagrangian just for the 1D sector that I can use to compute correlation functions in the 1D sector without having to worry about the 3D theory?
Sorry, Q and Q tilde were what again?
Q and Q tilde, Q is Q1 plus x over 2r Q2, and Q tilde is Q1 tilde plus x over 2r Q2 tilde, all inserted on a line, on the line.
Little q and what was the tilde?
You took the star and you raised it.
Yeah, that's right. Q tilde A is QA conjugate. Yeah, okay, good. Thank you. Okay. So the question is there a Lagrangian for this, for just the 1D sector by itself? Okay. So let me erase here. Maybe before I actually show you what the Lagrangian is, so today I'll just do the Higgs branch theory. And maybe before I do that, maybe I can make two comments.
Sorry, and before you talk about the Lagrangian,
Yeah.
Do you know the answers already? So there are a bunch of numbers, right?
Yeah.
And you already know
No. In
That's
this,
what you want to find.
yeah, that's what I want to find. I want to find in this class of theories, gauge theory with hypermultiplet matter, I want to find what the correlation functions are. We don't know what they are. We know what they are only in the free theory so far. And I want to know what they are both for the Higgs branch and for the Coulomb branch. And for the Coulomb branch, it would be extremely complicated because we'd have to compute correlation functions and monopole operators. Good luck with that. Okay, so comments. So the comments apply both to the Higgs branch and the Coulomb branch. The first comment is that n smaller or equal than 3 point functions in 1D, from them we can reconstruct these correlation functions in 3D of the more general operators.
because the position depends.
Because the position dependence is fixed and because the R symmetry structure is fixed for correlation functions involving at most 3 operators. If it's more than 3 operators, we cannot do that. But for at most 3 operators, we can. So computing correlation functions in the 1D theory, for instance, 2-point functions and 3-point functions, would mean computing OP coefficients in the 3D theory. So it's not that we're computing something only in the 1D theory. We can use it in the 3D theory.
Sorry, you commented on it before, but I missed it. When you compute the correlation function of these twisted operators, what is the R dependence of the overall dependence of the answer?
It has 1 over R to the sum of the dimensions of the 3D operators that the 1D operators came from.
So in effect, which combinations are being picked? Like
With, yeah, sure.
Is it half of this and half of this? That's what essentially is.
That's right. You have to have half of them should be ones and half of them should be twos.
Because one contract's okay.
Yeah, because one contracts with, that's right. Okay, good. And the other comment that I want to make is that this O in the 1D theory inserted at the origin, if you think about what this is in the 3D theory just O with all one indices. So this is a chiral operator in 3D. Because it's a chiral operator in 3D, it's associated with a holomorphic function. Let's call it F sub O on the Higgs branch or on the Coulomb branch, depending on which sector we're talking about. When we have holomorphic functions, we can take a product of holomorphic functions and we can get a holomorphic function. So there's a product on this set of operators, so I can define O1, O2 to be, there's a commutative product, O1, O2, would just be the operator that corresponds to the function FO1, O2, which is FO1, FO2. But we have another product, which is given by the OPE in the 1D theory. So this gives a non-commutative but associative product or a star product. So we define O1 of x, O2 of 0, say when x is bigger than 0, and we take x to 0. And this, we define it to be O1 star O2 of 0 as we take x to 0. So this, because it comes from the OPE, it's a non-commutative product. And what does it look like? Well, it has an expansion in 1 over r. So O1 star O2 is the regular product of leading order. And then there's a 1 over r term, and a 1 over r squared term, and so on. So in more abstract language, this 1D OPE gives a quantization of the ring of holomorphic functions on the Coulomb branch, or I'm sorry, on the Higgs branch or on the Coulomb branch, depending on which one we're looking at. Sorry, so this term is the regular product, and this term is a Poisson bracket of the two functions. Anyway.
Why does the star product have an expansion in terms of 1 over r?
Well, because the OPE has an expansion in terms of 1 over r. These operators were defined starting with the 3D operators and multiplying them by, adding various components, and some components are multiplied by x over 2r.
Yeah.
So then when we take OPs, we're going to have these powers of 1 over r. Yeah.
So the O1 star O2, what's the relation between the O1 O2 and O2 O1?
In general, they're different.
But so the underlying, primary parity symmetry,
Yeah.
does that have any implication about that?
Yeah, I think the odd terms here, when you switch them, these terms with odd powers of r would change sign, and the other ones won't. Okay, good. So now what I want to discuss is the answer to the question. So the Lagrangian for the 1D Higgs branch theory. So is there such a thing? The answer is yes. What's the method by which we find it? Well, there's two steps. One step is put this superconformal field theory on a round 3 sphere. And the second step is use supersymmetric localization. to find the answer. Maybe I'll keep that. So let me first explain what happens with the 1D sector once we put the theory on the 3-sphere, and then explain roughly what happens in supersymmetric localization and what the answer is. Okay? So for the first step, R3 is conformally equivalent to S3. On R3, we have a flat metric, dx squared. On S3, this gets multiplied by a conformal factor, which is 1 plus x squared over 4r squared, quantity squared. OK, so when I put the theory on S3, I have to have a radius for S3. And I'll take the radius of S3 to be the same as the parameter r that I had before. And that's the reason why I called it r, with hindsight. OK. And then what happens with so the topological sector in flat space was on a line. So it's 0, 0, x. And a line gets mapped under this geographic projection onto a great circle in the sphere, in the 3-sphere. That's parameterized by some angle phi. And the relation is that x is 2r times tangent of phi over 2. Now, the operators QA in flat space, say when they're at 0, 0, x, are not quite the same as the operators on the sphere. There's a conformal factor, wow factor. So the operator on the sphere, inserted at some phi, would be 1 over cosine phi over 2 times QA in flat space at the corresponding value of x given by this formula. And then what happens with the topological operator? So here we have Q1.
Yeah, I have a question here.
Yes.
Yeah. Are you using the same R? Is that R related to the R that was there earlier?
Yes, I'm using the same R as before, yes. I don't have to do that, but it simplifies the formulas to do that.
I see. Okay, thank you.
Mm-hmm. OK, so in flat space, we had Q of x.
Phi is the angle along the circle.
The circle, yeah. So Q of x was defined in terms of the operators in R3, Q1 plus x over 2r Q2. If we want to write it in terms of the operators on the sphere, we have to multiply by this cosine phi over 2. So we get that Q of phi is cosine phi over 2 times Q1 on the sphere plus sine phi over 2 times Q2 on the sphere.
And the cosine phi over 2 was the statement that was a dimension half operator.
Correct. Yeah. The reason why I went through this in a lot of detail was that the appearance of cosine phi over 2 and sine phi over 2, because this implies that since the operators Q1 and Q2 on the sphere are well defined, if we multiply by cosine phi over 2 and sine phi over 2, we get an antiperiodic operator on the circle. This could have been anticipated from the formula in flat space. If we take the limit when x goes to infinity, this goes like something times Q2. When x goes to minus infinity, it goes to minus Q2. So when we compactify the line onto a circle, the operator will be antiperiodic. So this Q and Q tilde are antiperiodic on the circle.
So they double value those.
Right. This comes from the fact that we started off with a half integer spin representation of SU2H. For integer spin representation, this wouldn't have happened. OK.
So which means that the topological theory is defined in a double cover of this grid circle.
Right. If you want the fields to be single valued.
Yes.
OK. So the second step.
I'm sorry. Does that mean that on the suppose I think of the double cover?
Yeah.
Suppose I have an operator on the first cover passing an operator on the second cover. Does it go through? I mean, can I literally think of it like something?
No, every operator will come with its image on the second cover.
I see.
if you want to think about it like that.
Yeah.
Okay, so supersymmetric localization idea is that for a theory invariant under some supercharged Q, there's the partition function. If we want to compute some partition function, which is a path integral, the partition function doesn't change if we modify the path integral by a term, if we modify the action by a term that's Q of something. So say this is Q of some psi. And I can call this multiplied by some coefficient T. I can call this V if I want it. So the partition function is independent of this parameter T because the theory is supersymmetric. Okay? If V is positive definite, then we can take T to be very large. And the contributions to this integral come only from the points, the locus in field space where Q phi is 0. Is the smallest it can be. So then Z localizes onto configurations that obey this condition, that Q psi is 0. And then there's a simplified formula for the partition function. Instead of it being, well, it could be a simplified formula. It could still be very complicated. So this is just an integral over this locus where Q psi is 0. Psi depends on x, so we find what x is, and we integrate only for those over those values of x. It's e to the minus s evaluated on this locus. Q psi is 0. And there's the one loop determinant. And this is exact. In ideal situations, Q psi is 0 has a finite dimensional space of solutions. So Q psi 0 is finite dimensional, is a finite dimensional manifold. And then Z is a finite dimensional integral. These are the ideal situations. We reduce an infinite dimensional path integral to a finite dimensional integral. This works also with insertions as long as the insertions are invariant under Q. If they're not invariant under Q, this isn't going to go through. So supersymmetric localization was applied to theories of this kind. And the path integral on the 3-sphere was reduced to a finite dimensional integral. This is the work of Kapustin, Willett, and Yakov. So the S3 partition function is written like this. It's an integral over some variable sigma. So sigma lives in the Cartan of the Lie algebra. And there's two factors. So one of them is, looks like this. You can write it, 2 sinh pi sigma, and a determinant in this representation of 2 cosh pi sigma. So in this case, the action evaluated on the localization locus is 0. There's just one loop determinants. There's a one loop determinant coming from the vector multiplet and one coming from the hypermultiplet, and this is the answer. To be explicit, if sigma is in the Cartan, so it's a linear combination of the Cartan elements. So sigma I, hi, where hi are the Cartan elements. And then the determinant, this determinant in some representation of some function of sigma is defined over as the product of all the weights in that representation, and we take F and we evaluate it at rho I sigma I.
Sorry, this one might be too quick.
Yes.
So what they did was, not for your particular situation of the line and so on. What is it? What is it exactly they did? They evaluated this for
S3 partition.
The S3 partition function, yes. No operator insertions.
And for the adjoint, that would mean sigma I minus sigma j, basically?
Yeah, correct. And prime means that we exclude the zero, I equals j, yes. And this was obtained using localization. So in localization, you have to choose a supercharge Q. And they chose a supercharge that was part of an n equal 2 supersymmetry algebra. Didn't use the full n equal 4 supersymmetry algebra because they wanted to do n equal 2 theories. Or whatever, n equal 3, whatever they did. Okay, and this formula is not very useful because for what we want to do, because these operators Q of x are not invariant under the supercharge that they used. So we cannot, there's no possibility of inserting operators and computing correlation functions. So then what we need to do is obvious. We should do localization with a supercharge that's used to define this 1D sector. And then maybe we'll get a better answer. But I'm mentioning this one because there's a nice relation between the formula that I'll show you and this one.
But here, you can use their supercharge and consider operators that are closed under that supercharge.
Yeah, but in general, it's very hard to find local operators that are closed under a supercharge. Just because if there's a supercharge, the supercharge usually squares to a translation. And for an operator to be invariant under the supercharge, well, it should be invariant under the square root of the supercharge as well, so it should be invariant under that translation. So local operators typically don't do that. Yeah. So, okay, so what we did is localization with Q used to define the 1D sector, roughly. And I'll tell you what the answer is. So there's an integral over sigma, like there, and sigma is in the Cartan.
So is there a canonical way of choosing your psi, or do you have to be creative? A Q commutator psi in your localization.
Well, lambda times Q lambda dagger. That's the canonical way, where lambda runs over all the fermions. Just because when you act with another Q, you have Q lambda quantity squared, so that's positive definite. Okay, so there's again this determinant, but only for the adjoint. 2 sinh pi sigma. And then we don't have a finite dimensional integral because we can't have a finite dimensional integral. We want to be able to insert operators anywhere on a circle. So we want the one-dimensional theory, not a finite dimensional integral. So this thing is multiplied by a path integral over these fields Q and Q tilde that I defined that are anti-periodic on the circle. Well, maybe I can just write it like this. So dq tilde e to the minus s1d, where s1d is very simple. It's minus 4 pi r integral over phi q tilde dq d phi plus q tilde sigma q. Okay? So this is a Gaussian theory in Q and Q tilde. By the way, there's a subtlety here. The integration is not over independent values of Q and Q tilde. It's over half-dimensional subspace in the space of complex Q and Q tilde. But that's not going to be important at all.
Sigma is not a field, right?
Sigma is not a field, yeah. So sigma is just numbers. So this is like a Gaussian theory of Q and Q tilde coupled to a matrix model.
Phi is the first term looks topological, the second term does not.
Correct.
Sorry,
The
sorry.
first term is topological, the second isn't.
Sorry.
Yes.
When you said the values q and q tilde take are not over the full line, but over half, you mean q should be q tilde star or something, or what do you mean?
That would be in an ideal situation, but the reality condition is more complicated than that and depends on sigma. But that's not going to be important for computing correlation functions. Okay, so Gaussian theory coupled to matrix model, if you want to call that a matrix model.
It looks like you have a Hamiltonian QQ. You get sigma QQ bar.
Yeah. Okay. Another thing I can say is that this can be viewed as a gauged quantum mechanics.
I suppose the integral over sigma makes it topological.
No, in general, okay, I'll explain that. But first, let me make another comment, which is that we could have thought of this as introducing a gauge field and having integrals over q tilde, and a 1D gauge field. And then the action could have been q tilde d phi q plus q tilde A1D q, where A1D is a 1D gauge field. 1D gauge field on the circle can be gauge fixed to a constant, and the Fadeev-Popov determinant for that gauge fixing is exactly this. So this is a 1D gauge quantum mechanics.
Sigma was this A.
Yeah, that's right. But this 1D gauge field is not related to the, doesn't only come from the gauge fields in 3 dimensions, it also comes from the scalars in 3 dimensions.
In the gauge multiple.
In the gauge multiple, yes. So the reality conditions are a little funny. It would be very interesting to understand those. And another thing what I wanted to say is that if we do the integral over q and q tilde, so if we actually, the Gaussian integral, we can do it, we get 1 over determinant in the representation R of 2 cosh pi sigma, which is what was missing to get the Kapustin-Willett and Yakov matrix model. So essentially, in the Kapustin-Willett Yakov matrix model, we took this determinant in the denominator and we expanded as a 1D theory. The advantage of that is that now we can insert any q's and q tildes that we want.
So does that become covariant derivative?
It's a covariant derivative, yeah.
Sigma is the, I mean, isn't it d by dt plus a, where a is sigma?
Yeah, that's right. That's exactly right.
So the whole action is just q covariant derivative q.
Yeah,
Because
but
that
you
goes-
might notice that I didn't put an I here,
Yeah.
and that I is not an error on my part now. It shouldn't be there. But
So it's not
yeah,
complex.
so
effect.
that's right. So the reality conditions are a little weird. But that doesn't matter. For computing correlation functions, that's irrelevant.
So how come you started with your Q and got the localization locus of their Q?
No, it's not the localization locus of their Q, because I got a more complicated theory. But, of course, I mean, that's the answer for the S3 partition function. It's clear that that's the answer. So I should be able to reproduce that answer somehow from my computation too.
So happens
And
that
this
you
is how
have
you
to
do it.
do
Yeah, that's right. Okay, so we don't need this anymore. And the way to compute correlation functions now is at fixed sigma. We can use the propagator for q and q tilde. So g sigma phi 1 minus phi 2 is this q of phi 1, q tilde of phi 2 at fixed sigma. And this is minus 1 over 8 pi r sine of phi 1, 2 plus tanh pi sigma times e to the minus sigma times phi 1 minus phi 2, or phi 1, 2. Phi 1, 2 is phi 1 minus phi 2. So the way to compute correlation functions after we do put insertions of q's and q tildes, we first work at fixed sigma. Fixed sigma, we do Wick contractions using this propagator, and then we do the sigma integral.
And at fixed sigma, you're not going to get topological. The tanh sigma
At fixed sigma, you actually will get topological correlators, only if you put in gauge invariant operators. You see, if I put, for instance, I have a q and a q tilde. To make something gauge invariant, I have to multiply by some q tilde of phi 1, and maybe, you know, and that's going to cancel the sigma dimension.
Of a gauge
Depends.
invariant operator is ordinary derivative.
Covariant derivative of a
The
gauge.
sigma came because it was covariant derivative.
Yes,
Covariant derivative knew which representation to transform.
that's right.
But when you did covariant derivative of something gauge invariant, it's just ordinary.
Yeah, that's right. That's right. So that's how it works. So you don't have to do the sigma integral in order to see that it's topological. Okay.
Phi 1 and phi 2 were meant to be angles, not hyperbolic angles, right? So your formula has or minus.
My formula has some problems.
So, yeah, there should be an I or something there, or what? I mean, I'm saying that
No.
phi 1, 2 doesn't.
This formula is correct if phi 1, 2, it goes between minus pi and pi. And you can check that if you put in a pi and you put in minus pi, this function is the same. Sorry, it's this function is anti-periodic. It has to be anti-periodic because Q is anti-periodic. Q and Q tilde are anti-periodic. So, but it's plug in pi, and then plug in minus pi, and then some algebra shows that the correct is the correct propagator with the correct boundary conditions. Okay. Good. So, brief example. I mean, that's essentially what I wanted to show you. I wanted to show you that this formalism. So just a small example. So super QED. So U1 gauge theory plus n hypers of charge 1. So in this case, the theory Z is there's just one sigma. There's n q's, n q tildes. And we have e to the 4 pi r d phi q tilde I d phi q I plus q tilde I sigma qi. So if we want to do this integral, we get 1 over 2 cosh pi sigma to the power n. So if we want to compute, for instance, q tilde 1, q2 of phi 1, and q tilde 2, q1 at phi 2 as an example. This is 1 over z if we want normalized correlators. And then we just use Wick contractions at fixed sigma. So we have this propagator g sigma of phi 1, 2, and g sigma of phi 2, 1. And because one of them is phi 1, 2, the other one is phi 2, 1, then the sigma dependence from this thing cancels. Divided by 2 cosh pi sigma to the power n. And you can find what the answer to this integral is. And this is minus n over 4 times n plus 1, 1 over 4 pi r quantity squared.
Wait, but did this
And you can do-
the tanh pi sigma also cancel? Before doing the integral?
No, the tanh pi sigma doesn't cancel. But it doesn't depend on phi.
It doesn't depend on phi.
So it's still topological.
Yes, phi. Yes. Depend on phi is the angle. not
Phi is the angle, yeah, that's right. Okay. And then you can do other examples. I will use this example actually tomorrow to describe the holographic dual of this theory.
This last formula looks like Wick's theorem, although your theory is very complicated.
Yeah, but there is Wick's theorem at fixed sigma. Because at fixed sigma, the theory is Gaussian, so I can use the Wick's theorem. And then and then I just have to do the integral over sigma, and that's slightly non-trivial. Okay. So there are generalizations.
So if the
Yeah.
number of flavors goes to infinity,
Yeah.
we should be able to see that we get just the free answer, results consistent with just free answers.
Well, I suppose that should be true. Is it? If I did the algebra correctly, that should work.
That's because
NF goes to infinity is essentially free.
Yeah, you can use 1 over NF perturbation theory. So leading order is just a free theory. That's right.
this n over n plus 1 goes to 1.
And that's right. Presumably that's important. Yeah. One can make the theory not conformal. So one can introduce either Fi parameters or mass terms, real mass. Okay. And one can still find a sector, and one can still, the computation goes through. It's just the 1D theory gets modified slightly.
Right. Now you have various different orderings.
Yeah.
Where is that? Where am I seeing that here?
In the theory?
No, in
sorry.
the answer. So suppose I could put all the q tildes.
There's a sign problem.
It's a sign.
Yeah, so the orderings, yeah, so in the 1D propagator, there's a sign phi 1, 2.
So but the magnitude of the answer is the same for all, and then there's just some sign.
No. No, if we have multiple operators, the answer could be different.
I see. So
But in this case,
number
there's just 2 operators, and it just so happens that this is a quadratic in Q, so they're periodic. So the answer is just a number. It doesn't depend on where the operators are, and doesn't change sign.
But in general, there's a complicated function of the ordering.
That's right. That's right.
And that the answer, the ratio of the answer to the free answer depends on the ordering.
The
I mean, if I
ratio.
take the n dependence is the only parameter. Let's say I've got n flavors of u1.
Yes.
The only parameter in the problem is n.
Yes.
When n goes to infinity, you get a free answer.
Yes.
So it's like the question is how does it behave like it's a function of 1 over n?
Sure.
Okay. So now I wanted to understand is there an overall coupling dependence times the free answer, or is it different for different orderings?
My guess is that it could be different.
Free answer also depends on the ordering.
The free
Yeah,
answer
it also depends on the ordering. But he's asking if it's the same dependence on the ordering.
In the limit.
No.
Not in the limit at all n. I don't think that's true. You can't see it from the simple example, but I'm sure I can construct an example where that's not true. Yeah.
The question was, you've got one parameter in the problem, which is 1 over n.
Yeah.
But now you've got many, associated with any particular operators, you've got many orderings. Right? So for any one set of orderings, you get the free answer times some number. But is this number dependent on which ordering? This function of 1 over n dependent on which ordering? Or is it just overall answer?
Yeah, I think it depends on, it changes the relative answers for the various orderings independently, in general.
Now it
Because I think even from this Wick's theorem, right? I mean, if you have 4 operators there,
Mhm.
you do all the contractions, and then generally speaking, you will get different coefficients in front of different contractions.
Yeah, yeah.
So if I chose different orderings, I get different numbers, or just their signs change?
Different numbers. Could be different. If it's just up to 3-point functions, you just the sign changes. But if it's 4-point functions or more, you can get different answers. Not just signs.
That seems to, then there's sort of very interesting consistency things, right? Analog Yang-Baxter stuff, that you get to this, starting from a canonical ordering,
Yeah,
you get to
yeah.
some ordering in
Yeah.
multiple ways, and
Yeah,
you get
that's
the
right.
same answer, and there
That's
seems to be a lot of.
That's right. We haven't explored that. Yeah. Okay. So I wanted to say that one.
You don't have conformance.
Yeah, that's right. That one can add various parameters that break conformal symmetry. And why was that possible? Well, it's related to why it was possible to do the localization computation at all. So in flat space, the supercharge that we used was a linear combination of Poincare and a superconformal charge. But once we map it to the sphere, it just becomes a Poincare supercharge on the sphere. So with it,
Rotation of the sphere.
rotation, well, the supercharge squares two rotations on the sphere.
Yeah, yeah.
So it's not necessary for this construction and for the localization computation to have conformal invariance on the sphere. So we can break conformal invariance on the sphere by introducing masses and Fi parameters. Of course, this mass deformation on the sphere is not related to the mass deformation in flat space.
So you can do it for any theory that preserves 8 supercharges on a sphere.
Correct. Yes, that's right. I can tell you one cute thing about the mass.
Is there an analog on the plane?
Sorry?
Is there an analog of this deformation? This is the mass deformation on the sphere.
Yeah.
And for that you are doing all these calculations.
I assume on the plane it will be some position-dependent deformation that one could potentially write down, but I haven't written it down explicitly.
The existence of SU2/2 is what it is.
No, it's actually the existence of SU2/1 times SU2/1. That's the algebra. This is a superalgebra that's preserved on the sphere. SU2 times SU2 is the rotational symmetry, and there's two U1R symmetries.
That's the conformal.
This is, no, not the conformal. This is the n=4 non-conformal algebra on the sphere. It only has rotation generators, SU2 times SU2. Well, these two SU2s, each SU2/1 admits a central extension, one parameter. And so these are the two parameters, M and the mass and the Fi parameter. Okay. The introducing the mass parameter is very easy. You just take sigma and replace by sigma plus mass in all the formulas. I can say why that's true. The real mass is associated with the flavor symmetry. So it's just the mass is just an expectation value for some scalars in a background vector multiplet. So then these Q's transform in a representation of G times the flavor symmetry group. So what I mean by this means sigma. So sigma is a matrix. I can think of Q as a column vector, and Q tilde as a row vector, and sigma as a matrix. So what sigma plus M means is that sigma times the identity in sigma for G times the identity in GF plus identity times M in GF. Anyway, it's simple to introduce mass parameters. I think I should probably stop. I mean, I could show you that the fourth derivative of the S3 free energy with respect to the mass just gives some OPE coefficient in this case for n equal 8 theories. So there's a fact that I used yesterday. It's like I probably should stop though. But maybe I can say one thing. The S3 partition function, maybe it was obvious from the localization computation, that the S3 partition function is the function of the mass is equal to the partition function in the theory in the 1D theory as a function of the mass. So then taking derivatives with respect to the mass means computing integrated correlators in the 1D theory, but integrated correlators in the 1D theory are very simple.
This is because the sigma Q tilde Q term, right?
Because, so what I computed the S3 partition function here. So these formulas are for the S3 partition function. But it's also the partition function of the 1D theory. That's all I'm saying.
And now
Yeah.
this statement, the derivative with respect to M is getting related to because sigma is like the sigma is coupling to Q or Q tilde Q.
Yeah, that's right. So then taking the derivative with respect to the mass computes correlation functions of these Q tilde Q's that the M couples to. And these would be very simple to evaluate. And because in this 1D theory is just half BPS multiplets from the 3D theory that contribute, then these integrated correlation functions can be written in terms of a linear combination of finitely many OPE coefficients squared.
This last equation, I thought that the right-hand
Well, I can call this, sorry, I can call this the whole thing S1. That's what I meant. Yeah. So this will have an extra term that depends on M. Yeah.
So you could, here you also add to this one-dimensional quantum mechanics some terms which are Q poles, right? So because of the Lagrangian by Q pose terms,
Yes.
which would be analog, which would be more deformations than J and M.
Then the Fi and the real mass deformation. Yeah, you could.
Element operators.
Yeah, you could also consider like these things squared or things like that. Yeah, that would be more deformations you can do. Yeah, but these are two deformations that are, well known. Oh, okay, that's all. I don't want to take more time.
Questions at HRI?
Yeah, can we explain once more why you have difficulty for Chern-Simons theories?
Because there was no off-shell formulation for the Chern-Simons, well, for the right type of vector multiplet that allows for a Chern-Simons interaction.
Yeah.
That's the difficulty. It doesn't.
I see.
It doesn't. You cannot have a Chern-Simons interaction with just vector multiplets. You need to have vector multiplets and twisted vector multiplets. But then you'd have two different gauge groups. If you wanted to have a single gauge group, then I don't know what kind of multiplet you want to have.
But suppose you live with two different gauge groups. Suppose you wanted to do it for ABJ.
Yes.
Could you do it there?
Oh, sorry. The two different gauge groups have to be abelian. Because otherwise you can't have a mixed Chern-Simons term between them. So I can do abelian, mixed Chern-Simons terms between abelian gauge groups, but I don't know how to do a single gauge group that's non-abelian with a Chern-Simons interaction, because I don't know how to describe the theory in an off-shell way.
So, Kapustin, when they wrote down the matrix model, they did the deformation by the Chern-Simons term was just a classical piece, right?
Yeah, that's right. That's right.
If one were to guess.
So you could conjecture, right? So you could conjecture that the only thing that changes in this case is that you multiply this by e to the I k sigma squared. I don't know if this guess is correct or not. One can try to test it in various examples, but that would be the guess.
The topological nature would still be preserved because this is only affecting sigma.
Yeah, in this theory, but if you have more complicated theories, well, it gets more complicated because you have to supplement. Maybe you want to consider operators that are not gauge invariant and then supplement them by monopole operators so that the whole thing is gauge invariant. So then it becomes very complicated. Yeah, this is something that we've been thinking about doing, but we wanted to understand the simpler cases first. So here I explained the Higgs branch story. Tomorrow I'll explain the Coulomb branch, also for these theories. Yeah, and then tomorrow I'll also talk about the holographic duals of these 1D theories.
So the supercharge that the Higgs branch localization uses is different from the one that Coulomb branch localization uses.
Yeah.
So
That's
you
right.
cannot do both these things.
Correct. Yeah, that's right.
HRI, more questions?
Well, the problem is that you are not able to hear very much. So even if we ask, we will not be able to hear back. So maybe tomorrow we'll ask the questions.
Well, Silvio is now standing nearer the mic, so if you could you try talking? Can
Yes,
you come?
sure. Yes.
Can you hear him now?
No, we cannot hear you very well actually.
Okay.
Oh,
so
okay.
As the Kumbh Mela peters out. Okay. 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 I have.
Okay, see you.
See.
Yep. Yep.
One or two questions.
Yes.
Firstly, for the D2 brain theory, the M2
For the M2 brane theory,
Yes.
just M2 branes in flat space?
Yes.
Yes, because there's a dual description that is of this form. So in that case, you can, so this is ABGM theory at level 1. You can also think of it as a UN gauge theory
Yeah.
with an adjoint hypermultiplet and a fundamental hypermultiplet.
Yeah,
So
the
then
D2,
it's,
D2
so
brane. Oh, I was thinking just about the D2 brane. No? Just an adjoint.
that theory, okay, that theory is subtle. That theory is bad. But it's supposed to flow to the
Yes.
same infrared fixed point as the theory that I just described that has an additional fundamental.
Okay. Why is that theory bad?
If you naively just compute the S3 partition function, it diverges. So that means that there's some sort of symmetry breaking.
Meaning it does not flow to it?
No, it does, but well, I can say it intuitively. Intuitively, D2 branes, if we lift them to M theory, we get M2 branes that are smeared over a circle. But the M2 brane theory should be where the M2 branes are localized at the point on a circle. So that thing is non-trivial. Maybe I should say that if you take, for instance, just pure U1 gauge theory, and you try to apply this formalism, doesn't work. The S3 partition function is just an integral over sigma with nothing else, so it blows up. But we know that there is a good IR fixed point, which is a free hypermultiplet.
Right. So it's the same thing. It localizes at a point.
That's right. That's right.
Circle space.
That's right.
Right. Okay. One more question. Going back to something Abhijit asked right at the beginning. Actually, could you say which is the, I mean, do you have a canonical non-abelian theory that you have in mind when you do this? Is there some theory
I don't have a canonical one in mind. I could consider any.
Okay. The question I wanted to ask was the following. As Abhijit said earlier in the talk, you're getting lots of numbers.
Yeah.
And those numbers tell you something about the OP, something about the correlation functions beyond 3-point function of the underlying theory.
I think that's wrong. I think it just tells you about the 3-point functions of the half BPS operators in the underlying theory.
Oh, then why is there so much interesting information with these various orderings?
It could be that it looks like there is interesting information, but presumably you can obtain everything from the OPE.
From the OPE?
In the 1D theory. I mean, that's certainly a true statement, right? You can use the 1D OPE and then reconstruct any correlation function in the 1D theory. And the 1D OPE is very simple in this case because there's just a finite number of operators that appears in the OPE expansion.
Oh. So suppose I had something with 4 operators.
Yes.
It looks like it's taking a particular kinematic section of the real 4-point function.
Yes.
Of the real theory.
That's right.
And you're saying that it only captures the exchange of the single trace operator.
Not necessarily single trace, half BPS.
Right. Of this sector in the middle.
That's right. So another way of thinking about it, suppose you have the 4-point function in the 3D theory, you expand it in superconformal blocks, and then you do the projection to the 1D theory. You'll find that most superconformal blocks give 0, except for the ones corresponding to half BPS operators, which give something non-zero.
Okay.
Conform blocks also, the non-supersymmetric ones also go away.
Sorry?
The non-supersymmetric ones also go away. The long multiple.
The long multiplets go away, yeah. They don't go away conformal block by conformal block. You have to add together all the conformal blocks in a superconformal multiplet. But after you do that, they go away. Yeah.
I see. So this, I see. So you say that we're only capturing information of 3-point functions between BPS, BPS, and BPS.
Yes. Before you deform, it could be that the deformation by an FI parameter, for instance, would capture slightly more information than that.
I see.
Yeah, I mean, I'm pretty sure it would.
Okay. In the situation of the M2 brane,
Yeah.
some of these BPS operators, as you said, would be multi-trace.
Yes.
Is the are these 3-point correlation functions something that is interesting from the point of view of gravity? I mean, there's information in that, right?
There's
Single trace,
information in
single
that.
trace, multi-trace.
Single trace, multi-trace. Yes.
There's information that would be non-trivial.
That's right, that's right. These would be some OP coefficients.
And one could check that it's some large n limit, they're what you get from gravity.
Yes, presumably yes. Yes.
And then when you deform away, it's more non-trivial then.
Yeah, absolutely. Yeah, for these OP coefficients, you can get formulas that are that involve area functions that are all orders in 1/n, presumably. I mean, we've done it for a couple examples where it's related to the derivatives with respect to the mass parameter. Yes, there's a lot of information in them, perturbatively non-over n and also.
We'll just,
Yeah.
I was hoping this, but you can't do the Chern-Simons. I was hoping to make contact with Vassiliev theory.
Okay.
There's this, it's something you can't do yet, but there's this m over n expansion. Un.
Yeah.
In a limit where you take n large but m fixed,
Yes.
the theory becomes another n. It becomes Vassiliev theory.
Yes.
But you need to be able to do that theory.
You need to be able to do Chern-Simons terms. That's right. Maybe it's possible to. I mean, the complaint that I had about the Chern-Simons theory was that you can't write down an off-shell formulation. That preserves the n equal 4 algebra. But to do localization, you only need one supercharge. You don't need the full n equal 4 subalgebra, n equal 4 algebra. So maybe it's possible to still be able to localize those theories, but we haven't thought about it.
Thank you.
Yeah.
This kind of localization to a lower dimension, can this be done, or has this been done for the 4 dimension or n equals 2 theory, which is the chiral algebra?
Only for the free theory. Yeah, there's a paper by Wolfgang Pillars and somebody else, I don't remember the name. They had some problems with the vector multiple localization.
Oh, so this is not. There were all these early papers by Nadar, Drucker and company, computed correlation functions of this sort, n equals y. That does not.
It's different operators, yeah.
Okay.